Jara, and are you also with somebody in ME? Are you shared by people?
Yes, a big group.
Okay, all right, so shared by a number of people. This is some work that Sam worked on during his PhD work, so he did his master's and his PhD at Oregon State, and has been here for the last month or so. So very much looking forward to hearing about this work and maybe hearing a little bit about what's coming up as well. So
I didn't prepare that. So.
we'll ask you that in some questions. Good, well thank you.
Yeah, thanks. So this is going to be pretty similar to my PhD defense, so lots about the transition of tsunami-like waves from basin to outflowing channel. And I think in any other format, my advisor Harry would be a co-author, but yeah. This is a broader audience than I normally present to, so if I gloss over something that you're like, wait, I don't know what that is, please feel free to just jump out. Should be 30, maybe 40 minutes, depending on how I pace it. So today I'm going to be talking about some idealized experiments, talking about a flat bottom, vertical walls, turning off the HVAC in a room to prevent small waves from forming on the water surface, and all other kinds of idealizations. But before I get into that, I want to talk about the motivation for these experiments, which is tsunamis entering rivers. Tsunamis often have different forms in rivers than a nearby dry land or ocean. And just an example from the 2011 disaster in Japan, the survivor was able to capture a video of the tsunami making landfall. You can see it has qualitatively different characteristics here than on the dry land. And that survivor was able to make it through the disaster because they were up on a coastal bluff. Back to the idealized experiments. We subdivided an existing wave tank into a wide basin and narrow channel with vertical walls, and it's completely flat. And we configured a flow generating system on the right here to send flow down the channel and create a shallow jet in the basin. And then that flow goes through some porous walls on the sides of the basin here and returns to the intakes of that flow generating system, creating a circulating flow. This allows me to keep a constant water level in the channel and basin for some nice repeatable experiments. On the left, I've got a piston-style wave maker that's going to create those tsunami-like waves incident upon the channel and on the vertical shoreline wall. Most of my experiments are with a water depth of 5 centimeters, so really small scale stuff. Roughly a commercial kiddie pool. So with this setup, what kind of parameter space are we looking at? My channel, I'm doing a width to depth ratio of 4.6, which is quite modest. Real rivers should be looking at 30, 60, or maybe hundreds for some of the larger rivers. But what I gain from using that really modest channel width is that it's on the similar length scales to my idealized tsunami-like waves. And that's going to be true with real tsunamis where they have these massive length scales that are at least as long as real river width. And for the outflow, I'm targeting a crude number of 0.1, which means the flow speed is about 1/10 of the shallow water wave speed. And that's actually about right for tidally dominated estuaries because those tides move with roughly the wave particle speed, drawing that flow out. So for our tsunami-like waves, we use solitary waves, which are sort of the traditional choice, and they're really great because they're repeatable across laboratories. You get really good agreement between experimental data and theory, and there are these isolated waves, so you can send one solitary wave down the tank. We're also using undulator bores, which are great because they've actually been observed in real seismically generated tsunamis. And this is an example from 2016 in Japan. You can see undulator bore-like formation going up the Tsunoshi River there. These are not as common with piston-style wave makers because of some practical challenges, but I really like how they have some realism to them. Right, so with this setup, what do we expect? In the offshore, we're going to see that the incident waves are focused onto that opposing shallow jet. And as the waves get closer to the transition, the discrepancy between the waves transmitted into the channel and reflected from these vertical walls is going to diffract wave energy towards the channel, further focusing those waves into it. And then finally, that very three-dimensional, complex-shaped wave that gets transmitted through is going to gradually become uniform as it propagates upstream, and eventually have this 1D wave behavior. So, let's start with the outflow jet. This is the flow generating system. I like to call it Mr. Octopus because it's got 8 wiggly bits. There's two symmetric intakes that go through a rotometer and globe valve, so I actually set the intake. And then the outflow through here is driven by gravity through another pair of rotometers and globe valves through 5 individually controllable discharge pipes that let me make sure that the flow that's going to the channel is uniform. In the channel itself, I've got these rigid mounted discharge conduits that are set to the mid-depth. It lets me distribute that flow evenly across the channel. Even with all that, I still get these turbulence-generated waves at the nozzle, so I've got a screen that helps suppress them and keep them small. I called these porous walls, maybe punctured wall is a better name. It's just some holes and some plugs that lets me manipulate the area and location of the return flow through the basin to try and minimize the effect on those waves propagating past it. These types of jets have a significant spatial variability, and I'm shooting for this constant flow rate. So to capture that spatial variability, I'm using particle image velocimetry. I've got a camera with a top-down perspective of the flow, and I'm seeding the flow with these slightly pointed particles so that I can measure those velocities on the water surface. So just right on the water surface. And what that temporal mean spatially varying profile looks like is over here. So again, I'm targeting the fruit number of 0.1, which is that size arrow. In the channel, we've got this uniform flow with a slight contraction near the outlet and then a gradual expansion as you go away from the basin. These type of expanding shallow jets will entrain flow from the side, and so you get this recirculation as the flow is drawn into the side of the jet. But that's not from a changing water level or anything like that. I only measured one side of the basin, but it should be the same on the other side. So these types of shallow jets often form large-scale coherent 2D oscillations or meandering patterns. And from the PIV data, I can look at the temporal variability in space. So this is the standard deviation of that series at every location. And we see that the variability is small along the center line of the jet, but large on the edges. And we expect that because this is fully turbulent flow with a reference number of about 3,300. And where that flow entrainment has, there's going to be some amount of mixing and variability. But those fluctuations remain small and local. If there was meandering here, we would see this variability all across the breadth of the jet. So how does that jet change the waves as they're propagating in? Well, to measure the wave profiles, I use the planar laser induced fluorescence method, or PLIF. With PLIF, you start with a laser and you create a laser sheet with a Powell lens, and then we bounce that laser sheet down to be plumb with the water surface, so the intersection of that laser sheet and the water surface is what I'm imaging. And with a physical filter and some dye in the water will glow and fluoresce from the laser light, and I can separate that out with the filter and then identify this water surface really quite accurately. These types of line measurements, it's kind of difficult to vocalize a location, so I've got a location reference in the bottom right here with that quiver plot that I showed you a little bit earlier, and this big red line to talk about which laser line exactly it is that I'm showing data from. These types of images, a lot of times they have artifacts and little troublesome details from the lab. So I spent some time dealing with a lot of the artifacts that I saw. So if you're a student here and you're dealing with these kinds of things, check out my code, it might help you. Right. So I want to look at one particular solitary wave case and kind of talk through the details, and then I'll zoom out and look through some other wave cases. And so with the case of an amplitude of 0.2 at the wave maker, and with a transverse transect, so I'm looking at the variability in this y direction of the wave profile. Here I can show the temporal evolution and the spatial evolution of the wave. And when we look near where the jet is acting, we see that the wave crest is lagged, that it arrives a little bit later on the jet, and that the amplitudes are larger. And so that's a focusing effect due to the opposing jet. But we also see that as a result of that changing waveform, that it's radiating a small wave out behind it. And to try and call that out here with a couple of transects, on the center line we can see that large amplitude and the lag relative to the flank. it's showed with the dashed line. And we can see this small radiating wave that looks like just a trailing hump in that time series. Yeah. So if we look at 4 cases, I did amplitudes from 0.1 to 0.4. We can see that the relative amplification, and here I'm using this form, this is percent change if you multiply it by 100, to show the relative change in the amplitude based on its original one. That essentially all of these solitary waves are amplified by the same relative amount, and it's not strongly dependent on their amplitude. But if we looked at the delayed arrival profile, that is the change in the shape of the crest line as it's approaching, if I normalize it with a time scale that's derived from the water depth, it's sort of inconsistent. But if I include the nonlinear parameters of those solitary waves listed here, but they're just functions of A over H, we can start to see their relatively consistent profiles in that change in shape. So I'm talking a lot about how they're lagged on the jet, but it'd be nice to be able to make a reasonable estimate of the change in speed due to that opposing flow. So I can track along the center line the position of that crest as it propagates forward and get that path to estimate the speed. If I normalize the time scale by something with water depth, really what dominates is that amplitude because the speed of these waves is dependent on their amplitude. But if I adjust by that theoretical speed, I get a nice collapsed line, but it's not quite on 1, it's slightly slowed down from the speed. It barely misses that corner, right? And so if I try to estimate that from the flow conditions, if I just take the depth averaged, because I'm measuring the speed on the center line, so if I just think locally, okay, I've got some 1/7 power law for my flow there, I'll estimate something like this, which is a pretty significant overestimate, not really a good predictor. But if I include the fact that this is a Gaussian-shaped shallow jet, and I integrate over the depth and the breadth of that, I can make a pretty good area averaged estimate of the actual measured change in celerity due to the presence of the flow. Because I've got like 1,000 data points or something there, these are really tight estimates, but they're not perfect. If your brain is screaming at you that there's some kind of meaningful trend here, these are all within that 95% confidence interval. And this one's slightly out, but it's not quite. Nothing significant, I don't think. Right. So, talked a lot about the change in celerity on the center line, but what about in the flank where there's a negligible amount of flow? Well, if I look in the no flow condition and I look at a transect that's close to but not exactly on the shoreline, and here I want to try and compare those, the arrival time in the flank, because I didn't take quite as dense of a measurement. And I want to go close here but not too close. You can see the reflected waves from the shoreline, but I want to ignore those for a second and just look at the arrival of the crest. Compare it in the no flow with flow conditions. And I measure a delayed arrival in the flank of 1.8. And if I estimate that area average change in speed, and I apply it over here, I can make a pretty reasonable estimate of that delay. So it seems like the area averaged opposing jet speed is applying to the solitary wave both on the center line and pretty far away from the action of that. So it's affecting this really substantially larger region than the jet itself.
Why is that the case?
Yeah. So I wasn't able to make a good, well, this was the best predictor I could come up with. But there's a few things that's happening over the flank. One is that there's a reduction in amplitude. And the speed of these waves is driven by their amplitude. But that, if I just use the change in amplitude, it doesn't get me a very good estimate. But it seems like it has something to do with how this amplitude is linked to the transverse profile. And so because they're linked, they must be traveling, well, they seem to be changing their shape slowly enough that I think a permanent form approximation over those short distances seems to apply. Yeah, this is the best answer I came up with. Next I'm going to talk about under the bores, but I know under the bores are not quite as frequent to see as solitary waves, so I just want to talk about them a little bit. You can see under the bore formations in all kinds of physical phenomena. Here's an example of wave clouds over the coast of California, where a thermal shock creates these long tube-like under the bore formations in that thermal density. In Australia, that same type of thing happens very frequently in the morning in this one particular region. They call them morning glories. And so people will go out, they're somewhat more predictable there. And you can go out and get these amazing photographs of those tubes. And in strongly convergent, high tidal fluctuation estuaries, you can get these tidal under the bores. And these are really popular with surfers because they're as predictable as the tides, and you can go catch a ride. And because of that pretty wide range of physical phenomena, this problem is really loved by mathematicians, and there's a lot of tools you can use to go out and describe and analyze these. The most general form is dispersive shock wave. And so for water waves, what you have is some rapid change in water level that I'm indicating with the dashed line here. And that change in water level creates oscillations about the shock. And this is lab data. And what's really great about that is they form naturally. So making them super easy, you just move your paddle at constant velocity. And as long as you start it up fast enough to create that shock, then those undulations will form all on their own. Of course, you have to stop most wave makers. But I wanted to call this out because you end up with this unique spatial front structure of under the bores, where you have this leading solitary wave-like formation. And as you go further and further back onto that plateau, you get these dispersive waves that sort of resemble more linear oscillations. And that front-to-back spatial structure will really underpin a lot of my analysis for these under the bores. Okay, so if we look at that same transverse profile off where it's really just the flow that's affecting the wave behavior, and we look at the tempora evolution on the jet, we see a lot of the same things as solitary waves: increased amplitude and a slightly lagged arrival from the flank. And this first crest looks a lot like a solitary wave, but as you go back, that mismatch in the arrival time of those trailing undulations creates this discrepancy where the peaks on the center line shown solid here, and the troughs in the flank shown with the dashed dot line here line up. And that leads to this interference pattern that happens somewhat near the edge of the jet that you can see here, and in the suppressed oscillations of the dashed line here. That happens around 8, which is about out here. So I say the edge of the jet, but that's not too literal. So if we look at that same data from a different perspective, here I have space and I have time. And I'm showing the amplitude of this wave relative to its plateau height. So I'm saying if it matches the plateau height, it's 1, and then all my troughs are in blue and my crests are in red. And I try to identify those crest lines because I want to talk about the amplitude. There's multiple amplitudes depending on which one you're talking about. And we can see this profile for the leading crest really resembles a solitary wave. And then those trailing undulations, if I follow the crests, have this trough, and you can see the node forming around here. The lagged arrivals of those trailing crests is really substantial, so substantial that we have a drop here in jump. And what I'm doing is I'm just picking a location and I'm counting the crests as they arrive. But that sort of indicates with these jumps that the crests are actually becoming disconnected. And so if I instead require that the crests be transversely connected by considering this spatial information as well, I can see that this crest here is confined to the flank. It doesn't actually span across the jet itself. And that's interesting for a couple of reasons, but one of them is that in roughly the same amount of time, I have 4 crests here and 5 crests over here, which indicates that the wave behavior on the jet is actually increasing the spacing between those crests. And so if I look at just the first 2 crests here, have a little bit more than this, but this is the clearest case, and I line up those second undulations, we can see that the distance in the no-flow case is less than in the with-flow case. So the opposing jet is actually increasing the wavelength rather than decreasing it, which is a little bit more frequent. What's interesting about that is it suggests that the speed of these crests is being altered non-uniformly. What I mean is that the second crest is slowed more than the first by the opposing crest, and that's what increases the space between them. So if I, using that same methodology from the solitary waves, if I track those crests along the center line, and I can compare the no-flow and with-flow speeds of those crests, and I can show the distance, the difference in those speeds due to the opposing jet. And the first crest is slowed down the least, and the fourth crest is slowed down the most. This fourth crest, that's pretty close to the 0.1 for number that I was targeting. And this is even faster than the solitary wave cases. But what that suggests is that it's the natural behavior of an undulator bore for those leading waves to separate out and eventually become solitary waves. But it seems like this opposing jet is actually increasing, exaggerating that process, and the leading wave is separating out even faster than it would without the flow. My tank wasn't long enough to see that. Okay. So let's talk about how these waves are transmitted. Try and take advantage of the video format here. So we've got these waves generated with the same wave-maker motions, and I'm looking at a transect along the center line. In no flow case, we see that clean solitary wave. In a with flow case, we see the larger lagged change in waveform due to the presence of the flow. And if we look at how this wave evolves as it intrudes into the channel, we see a rapid increase in the amplitude as it crosses, and then these reflected waves and these trailing waves are formed behind it. I'll let that play again. So that shows what's happening, not why. So if we look at a transect that's right next to the wall, just a half water depth away, we can see that there's this really big difference between the amplitude of the waves that are primarily transmitted in the channel, and primarily reflected. In the no-flow case, we see that amplitude get close to double, which is what you expect in perfect reflection. But in the with-flow case, we have this local maximum. And that's because the offshore condition for the with-flow case decreases into the flank. And so as you go further and further away, double actually becomes a smaller and smaller value. And that's what's driving that wave energy into the channel and causing that rapid amplification.
So this is lagged time.
Oh, sorry. Yes. This is the actual maximum value of the water surface, the amplitude, so to speak. But it doesn't occur at the same time.
See, you are shifting it to account for the later arrival time.
I'm just picking the biggest value. Yeah. Right. So zooming out, if we look at the other wave cases, and we look at that relative change in amplification, in the no-flow case we can see a slight reduction in amplitude from what I specified as the wave maker. These distances are long enough that the decay rate due to just friction and viscosity is really predictable. So we expect it to be a little bit less. And in the with-flow case you can see these substantial increase on the center line due to the presence of the jet. And of course the rapid amplification that's pretty near the transition at zero. But if you look, this kind of jump is kind of similar between these cases. So if I instead normalize by some offshore value, and I'm taking a reference at -12, and I'm just saying, okay, that's my AOF, that's my reference value, and if I look at the relative change in the amplification from that reference once it gets close into the channel, we can start to see a trend emerge, where the solid line in the smallest wave case always has the largest amplification, and the larger waves in the dotted line have the smallest amplification. And what's interesting, something that's interesting about solitary waves is that their length scales are linked to their amplitude. So larger solitary waves have narrower bodies. And so here I'm just normalizing by the water depth, and you can sort of see that. But if I include a factor of h squared root of h over a, with some constant, an arbitrary constant. I picked 2.12. And what I like about that is that it gets you, that 2L is 95% the volume of the solitary wave. And they start to look really similar on that length scale. So if I plot that relative amplification to the offshore condition versus the length of the wave relative to the channel width, we can start to be a little bit more explicit about that trend. And I've been showing you experiments with this channel width of 4.6, but I did some supplemental experiments with 2.3 to try and get that length scale longer and longer relative to the channel width itself. And in the black dots here, I've got the no flow condition, and we get this nice linear trend. And it's roughly equivalent to the trend in the with flow condition that I'm showing with red dots. And so it seems like this trend is a really good predictor of the amplification just due to that geometric factor, just the fact that it's transitioning in a pretty broad variety of wave cases and wave shapes, because in the with flow condition you have that pretty substantial change in wave shape as well. One more note on solitary waves. In the with flow condition, you have this really local peak in the amplitude shortly after it transitions in, and then it drops down. And so, what's up with that? Well, if we look at the transverse profiles in the channel itself, so I've got one right on the transition, just a half water depth in, and then 3 water depths in. We can see that at the entrance and just a little bit in, we have this really peaky behavior across the channel because of that 3D shape. But if we go far enough upstream, we start to get these really uniform profiles across the channel. And so that peakiness is just an artifact of my choice to measure along the center line. If I had averaged across it or something, it might have had a more consistent amplitude. Okay. We might be flying through this. So, yeah, sorry about that. So, the undulate bore. How does the undulate bore transition into the channel? Well, if we look at the center line again, and we look at how the bore is transmitting in, here in the no-flow case, we have that clean start of the undulate bore, and then here we have the amplified, lagged arrival of the undulate bore in the presence of the flow. And you'll see that rapid amplification of the undulate bores as they transition in, and then you have a really complex incident reflected pattern as those waves reflected interact with the incoming waves further on. And then here we've got total inundation of my measured region. So I'll go ahead and let that play out. But it results in essentially a larger undulate bore being transmitted into the channel. So if I want to talk about how they're amplified, I again have to talk about exactly what crests I'm specifying. And so here I'm doing the transversely connected crests. That one crest that was confined to the flank stays in the flank as it approaches the channel itself. And if we look at the amplitude of those crests, we can see the solitary wave-like profile for these leading undulations. And that the trailing undulations have a peakedness on the flank, both in the no-flow and the with-flow conditions. When I took this data, I didn't think to go so far. I went a little bit farther with the with-flow case. I assume I would see more peaks if I kept going, but just like in the with-flow case, but I didn't measure. So if we just look at the incident wave amplitude of those undulations, and I'm leaving a gap here where I wasn't able to separate out the incident wave amplitude from the incident reflected one, end up with these big misleading peaks. We can see that that structure, that front to back structure, is preserved in an offshore condition where you have that decreasing amplitude with subsequent crests, and that it's preserved as they're amplified across, and it's a little bit clearer here. It's tight there, but it holds the same pattern. And if we do the same thing where I pick some offshore reference location, in this case -20, and I plot the relative change in amplitude to that reference location, we can see that in the no-flow case that we have this increasing trend that each subsequent crest is amplified more and more than the previous one. In the with-flow condition, it's a little bit messier, hard to pull out that trend, but it just shows how that front-to-back structure is really playing a key role in how these waves are amplified as they transition into the channel. Right, so that's it for me. We created and implemented this recirculating wave tank. We showed how the opposing jet focused the solitary waves and under the bore as they propagate in, and that using the area average flow speed was a better predictor of the change in celerity than any local one. For solitary waves, the longest waves have the largest increase in amplification, and that for the undulate bore, each subsequent crest have the largest amplification. So yeah, thank you.
Great, thank you very much, Sam. We have some time for questions. There are some from the audience. Sam gets a call, he will not.
Justin.
Okay, Sam, thanks for your talk. So I'm not super familiar with like lab experiments, but when you have your outflow channel, does that have like walls to like a significant height? Like does that trap the flow in a way that isn't trapped in like real life? Like so do you have walls like extending up from your outflow?
Yeah, so let me pull up the photo there.
Sorry, I got the plan view, but I didn't.
No, it's all good. So the water depth, you can actually see the hard water line in the white here, is really quite small compared to the elevation of the channel walls. So even my largest waves don't, well, they had to be heavy and tall enough that they wouldn't move the wall.
Right.
Because out here there's no wave conditions. Is that what you meant?
Yeah, do you think that like if you had overtopping of the, like if you had a situation where your solitary wave was overtopping, how do you think that would affect, you know, anything that you saw?
I've seen in numerical estimates where if they have a grid that's coarser than the width of the river, what they'll do is they'll say, okay, we have an estimate to the left or right in the river, and we'll assume that the diffraction is strong enough that the amplitude, like the actual wave height is the same, but the river is deeper. So you end up with a taller like wave height relative to the water depth, but
Okay.
in terms of elevation, it's flat across.
Okay.
But that's a long way of saying that yes, absolutely.
Yeah, okay, thank you.
I wanted to know if that contraction you had in the jet is physically based, or is a matter of
Oh, it's physically
artifact?
based, and
Yeah?
boy, am I gonna love telling.
What would be
It's really quite interesting,
And
actually.
the other question I wanted to make is that did you have the chance to measure velocities with the waves, or it's too hard?
I didn't do that too hard.
Yeah. Okay.
So that contraction only occurs at the water surface. And so qualitatively with the dye study here, when I put dye at the water surface, you see this contracting V. But if I put the water deeper, it goes straight through. So it's actually an artifact of the fact that I'm putting slightly buoyant particles. And these types of secondary currents are pretty well established for air jets in really detailed measurements, more detailed than anything I'm doing here. But it has to do with how, so in air jets, if you have two solid walls, the contraction happens in the middle. But because of the free surface stress condition, you end up with a contraction at the water surface. And it results in a pretty unintuitive profile in depth where the flow speed beneath the water surface is actually larger. Well, all of this secondary current stuff doesn't seem to be the driver of wave behavior. So it's an interesting detail, but ultimately, because I'm so focused on the wave behavior, it doesn't seem to be a big driver of that.
And the difficulty in measuring the currents with the waves is because of what is transient. It's too fast.
If I used something like an ADV, it wouldn't be too hard, but it's just a point measurement.
Right.
Because I was doing, I did 1 meter by 1 meter panels. And when you do that, and I had to do that because it's such a large spatially varying profile, And part of the challenge of that is seeding. So if I show you my seeding picture here, somewhere, here we go. This seeding is not very dense. And there's a pretty significant sampling bias in that I have a ton of samples where the flow is significant because there's more particles moving through. But out here I might have like one particle sample. And in my case, because I know the flow is small, I can sort of average that out and deal with that uncertainty because it should be pretty close to zero and not super significant. But if I really cared about this region, this type of seeding would not be significant. So because of that and because of the biases of trying to get this seeding to be correct and how it would affect the elevation of the measurements, which is another trick with this laserless config because I have to account for the elevation of the water if it's not flat. Yeah, I think in theory it should be possible, but I wasn't able to do it. Yes?
I'm just wondering if there's ever been an observed or recorded event at the Columbia Bar. It's a fearsome place, I don't want to go to it. I imagine a tsunami would be really wild there. Has anybody ever measured that with a buoy?
I'm sure. I'm not that I can recall, but that feels very likely. And I avoided changes in water depth here.
I see.
I sort of designed this to avoid that aspect of the problem. I think it's better understood that this type of flow-based experimental design. But it should be, yeah, it should for sure lead to some interesting things. And I would not be surprised if there's been a study on that bar specifically. Yes?
Great talk, thank you. I'm curious if you had any thoughts, because in the image, I think it's just vertical walls, like at the coastline, pretty much.
Mm-hmm.
Do you have any thoughts of how, just kind of what would be different if you have different sorts of coastal infrastructure there, I know a kind of laboratory experiment, but moving into maybe what you'd see in your environment, maybe beaches or other kinds of coastal infrastructure that would then be extending into the water.
Yeah. Yeah, so there's, in terms of practical challenges, there's a lot of stuff. So I'll say it's not completely unfounded to talk about bluffs next to rivers, if only from this example, although it's pretty rare to have a bluff on both sides. And when you look at this type of braking, so I didn't do braking also, so that's going to be a big difference. But it does seem like a lot of that energy gets funneled in from the sides depending on the exact shape of the estuary. And a lot of times it's a lot more of a gradual transition than this very hard right angle idealization that I'm doing. But I think in general those fast but smooth transitions are better understood than this case. Yeah.
It talks. I had two questions actually. The first is maybe a bit easier. What I was really interested in is you were able to predict what the amplitude growth would be of the first wave. And you predicted it over a large number of cases based on the wavelength to breadth ratio.
Yeah.
And at first I didn't understand it, but I think it's a function of diffraction, is that right?
I think because of the way that I've set this up, that it's the vertical walls, it must be diffraction. Yeah.
Right. It just so happens that I was trying to read about diffraction recently, and that's exactly what determines the diffraction, right? The wavelength to slit ratio.
Yeah.
Yeah.
So there's a classic experiment from the 50s of a basin to basin through a gap, Penny and Price, where they show a similar, it's not quite linear, but it's a similar relationship how the longer waves have a bigger intrusion, which is what I base this on. But there's enough differences, the way they did it only works for, they did it for linear waves and these are solitary waves, so some differences. But yeah, definitely inspired by that type of classical work.
Yeah, and this is quite a predictive tool, right? You can predict what the amplification factor will be in the river, so that's awesome.
Yeah.
The other thing that was very interesting, but I don't know if you mentioned the predictive tool for that, was this extra crest that appears.
Oh, yeah.
Right?
Yeah.
So, kind of based on Ben's question, if you're, 3 channel widths away, suddenly you have an extra flooding event. And so, what can you say about that crest?
I think
Yeah.
I would interpret this as being one less.
Okay.
Because they're getting longer. So there should, this is, I didn't measure that far in the no-flow case, so I can't make a direct comparison, which I think would be really illustrative for saying this is just like it is in the no-flow case. I think it is, but I can't verify that explicitly. But because these are getting longer, I would interpret it as one less. Yeah, and no, I don't have a good prediction for it.
Yeah, I think it might be worth digging into the data to see what you might find, right? Like exactly, here it's scaled in terms of depth, but maybe the right scaling is in terms of width, or, I don't know, can we predict how far out that appears, what its magnitude will be, that might
Yeah,
be
I tried to do, under the assumption that so I couldn't do any numerical models with a stable flow, which I think is a me thing. I'm sure somebody can do it, but I couldn't. So I hoped that with a change in like an equivalent change in water depth, I could start to show this more explicitly. And there's a lot of similar features, but I have not yet been able to find anything super conclusive.
super interesting.
I have a question related to the flows that you are imposing to the system.
Yeah.
So, did you pick them like arbitrarily, or
Yeah.
are they based on, let's say, I don't know, a proportion of the flow speed of the wave?
Yeah, so a fruit number of 0.1 is pretty realistic for paddle-dominated estuaries. It can be more or less, like maybe 0.2. But this stability stuff is a pretty significant practical barrier in the lab. This is the only regime of stability I could get. If I went up to 0.2, it was huge. I mean, you get these huge meanderings. It's not subtle. And the issue with that is, so I don't even think I mentioned it, but where is that video? Like this is 9 trials. Right? So if I don't have super repeatable flow conditions, then I can't put these together and make good sense of it. So it's really important for the limitations of my lab that I have those really good repeatabilities. I do think that if you had different equipment, you could embrace that temporally variable flow and construct something a little bit better. But I, given my lab limitations, needed it to be quite stable.
Sorry, this is the average of 9 trials, or this is the best of 9 trials?
My camera only has a span of 6 water depths, so it's like
Okay.
some overlaps, but not everywhere.
In the figure where you were looking at the change in celerity as a function of the number of the crests, that black
This
bar
one?
graph, that one. How come there's not a big change between the second and third crest, but there is a big change between the first and second and the fourth? Is there a physical mechanism for that?
Hard to say. I have less. So at the first crest, I have the whole span. The second crest, I have maybe 3/4 of the span, and less and less and less. My uncertainties get bigger and bigger with each crest because I have less data. So my interpretation of this was maybe this one's a little high, maybe this one's a little low.
Okay.
But I don't, it must max out, right? Presumably, it's got to max out. I could only observe the speed up to the 4th crest. There are more that occur, but not that I could observe the speed of. And so I'm thinking that as these trailing undulations look more and more like linear waves, they're going to behave more and more like linear waves in that their speed is exactly the flow speed there. But yeah, with these more, I observed it, but I don't know, I don't have a good predictor for it.
Okay.
Oh, hi.
Hi. I think you touched on one back to ask when you answered Nimish's question. Are there any numerical models, analytical models, other experiments that you can compare your findings to?
For the no-flow case, there was some pretty detailed work on a very similar stuff for the solitary waves. Confusingly, I don't know what to make of the differences. There's some differences that the location of the amplitudes, the amplification is different, and then the actual trend of that length over width is different. The trend could be some kind of dissipation, but the location is the thing that I don't know how to interpret. In terms of the width flow, I couldn't make a stable model. Somebody probably could, but I couldn't.
Great, just one last question. So you're testing a case in which the flow speed of the jet is much smaller than the wave speed, no?
Smaller than the wave propagation speed,
Mhm.
but comparable to the wave particle speeds.
Right.
So the motion of the fluid, not the motion of the wave.
And that decision was made because of what?
A few things. If you try to make flows with comparable speeds to waves, you get weird stuff going on. Hydraulic jump would be one of them. Two, it's pretty unrealistic for rivers. This is the right regime. I would have liked to do more flow speeds, but as I mentioned earlier, I had stability issues. So this was the most consistent result, but I think going like a little bit lower and a little bit higher, but not like one, like 0.05 to 0.2. Right.
Lots of good questions. Any other questions for Sam? Great, well, let's thank him again for a really nice presentation.